Hello, everyone. My name is Melissa Hua, and I'm a current second year environmental science student. And my research project is titled Particulate Matter Estimates from Wildfires in the Western United States from 1950 to 2023. I was incredibly grateful to be mentored by Dr. Claire Schallert, who is a postdoc in the Department of Environmental Health Sciences, and Dr. Miriam Marlier, who is a professor in the Department of Environmental Health Sciences. So how have wildfires and PM 2.5 emissions changed due to climate change? Notably, due to anthropogenic climate change, the severity and frequency of wildfires has increased throughout the Western United States. And so one particular group that studies these impacts is the Western Fire and Forest Resilience Collaborative. And a diagram they made is shown to the right, which shows all of the different adverse consequences as a result of wildfires. In particular, we'll be focusing on the gear titled Consequences for Ecosystem Services, with an emphasis on air quality. So one pollutant that is often associated with wildfires is PM 2.5, which is particulate matter 2.5 microns in diameter or smaller, and is often associated with poor cardiovascular and respiratory outcomes due to its ability to infiltrate deep into an individual's bloodstreams. So how do we estimate PM 2.5 emissions? Traditionally, estimates have come from satellite models. However, these satellite models lack historical fire data prior to the 1980s, and they lack historical smoke data prior to the 2000s. Thus, Dynaforce, which was also made by the Western Fire and Forest Resilience Collaborative, henceforth referred to as WFRIC, is a landscape ecology model that can help fill in these gaps and simulates based on observational data from real wildfires. In particular, one aspect that can really impact the amount of PM 2.5 emitted is the type of vegetation. Thus, using Dynaforce, we were able to use the outputs from the fire effects and fire characteristics components, which you can see on the diagram to the right, to get a better idea of what PM 2.5 emissions look like across the Western United States. So the two questions that we'll be focusing on this research presentation is as follows. How does the type of vegetation impact the amount of PM 2.5 emitted across the Western United States due to wildfires? And two, how have these emissions changed historically? In order to conduct this research, we used 10 Dynaforce simulations to aggregate data. And this data focused on the burned area as a result of fires, the number of fires, the years of fires, and the PM 2.5 emissions across fires on a 1 kilometer squared grid cell. So typically, when we do PM 2.5 emissions estimates on human health, we use this four-step framework. In particular, this research focuses on the second block, which specifically emphasizes emissions estimates and calculating the daily emission. Using R, we were able to compare the relationships across plant functional types for all of the characteristics that I had indicated earlier. So what are PM 2.5 emissions averages across plant functional types? In order to study this, we created a box plot, which shows the averages in kilograms across each plant functional type. Although it's relatively uniform for most of the plant functional types, hemlock cedar by far has the highest averages, along with the greatest variability. So the dots represent outliers, and you can see that the distance between the highest and lowest dot is the highest for hemlock cedar, thus indicating the greatest variability. In contrast, let's look at five needle pine in the diagram, as denoted by the red arrow. We can see that not only does it have the lowest PM 2.5 emissions on average, but its variability is relatively less as compared to hemlock cedar and is situated around the 25 to 75th percentile. How have PM 2.5 emissions changed from the 1950s to 2023? We can see that in total, across these 1 kilometer squared grid cells, that amount of PM 2.5 emissions has substantially increased since the 2000s, with a particular emphasis and increase in the 2020s. Just to compare, let's look at 1988, which is also denoted by this red arrow. And this is actually an outlier year as a result of the Yellowstone fires. And we can see that compared to all the other years, it has the most PM2.5 emissions. But we can also see that the composition of which plant functional types contributed like a certain percentage to the total PM2.5 emissions for that year is so different than the 2023 one. For example, lodgepole pine makes up a significant percentage of this composition, but has almost like not as significant as a contribution in 2023. Thus, the composition for PM2.5 emissions across each plant functional type is not uniform. How have the number of fires changed from 1950 to 2023 for each plant functional type? So we can see that the two plant functional types that actually have the most are pinyon pine and interior Douglas fir. However, hemlock cedar, which has the highest average amount of PM2.5 emissions per grid cell, actually is not even close to having the most number of unique fires per year. And this is particularly interesting because the two plant functional types that have had the most PM2.5 emissions historically has been California mixed conifer and interior Douglas fir. And pinyon pine is not in that top two, which suggests that the number of fires does not necessarily correlate to the amount of total historical PM2.5 emissions. And another thing to also note is that across each plant functional type, there actually isn't a total increase in number of fires. Certain ones, such as aspen and Engelmann spruce fir and lodgepole pine, have actually seen increases, but plant functional types such as California mixed conifer and southern ponderosa pine have not seen increases. So this isn't necessarily uniform across plant functional type. So what was really interesting from the survey is that hemlock cedar burns less, but has the highest average PM2.5 emissions across grid cell. One challenge with this is that Dynaforce is actually an iterative model that will continue to be changed. And so the outputs might not necessarily be similar. And also to note, the data between 1950 and 1980s are simulated. So it is based on observational fire data, but it is not from actual fires themselves. And so we can see that across each of the plots, there isn't really a uniform spread or pattern. So future steps with this data is that we want to create spatial maps to show the distribution of PM2.5 emissions across plant functional types using QGIS. And so while we have a graph that earlier, which showed the distribution of plant functional types across the Western United States, we don't actually have a distribution of the emissions themselves and the severity of such emissions. Notably, the fires that we used are just wildfires. However, we want to see if there is a relationship between vegetation type and prescribed burns when studying emissions of PM2.5. And lastly, we focus on PM2.5, but there are other pollutants that are often associated with wildfires, such as PM10 and CO2, which I think would be so awesome to look at. In conclusion, Dynaforce provides a comprehensive view of PM2.5 emissions across the Western United States and opens us a door into fire data that we've never been able to look at, notably from that 1950 to 2000 data that just doesn't exist and that we're able to simulate using Dynaforce. We see that there has been a total increase in PM2.5 emissions since the 2000s that is linked to these wildfires. And lastly, we note that the number of fires does not necessarily correlate to the amount of PM2.5 emitted, both on average and in total. To end, I would like to thank my mentors, Dr. Miriam Marlier and Dr. Claire Schallert, for guiding and supporting my research. I would also like to thank the Sustainable LA Grand Challenge for their continued support in sponsoring my research journey. And lastly, I would like to thank the Western Fire and Forest Resilience Collaborative Group for their efforts in creating the Dynaforce model and for advancing fire research. Thank you so much and have an amazing day.